Hello, chemists. Have you ever tried following a recipe that only tells you percentages? Like 40% flour, 20% sugar, and 40% milk. Hmm? You'd be scratching your head. How do I actually make a cake with this? That's exactly what we are doing in chemistry when we move from percentages to formulas. The empirical formula is like the recipe ratio, while the molecular formula is like the actual ingredient count for the dish. So, when a problem gives us percentages of elements, we are not lost. We just convert them step by step into ratios, then into formulas. And if molecular mass or vapor density is given, we can stretch those ratios into the actual molecular formula. Let's see how this unfolds with real problems. Alright, think of this as your chemistry GPS. Step 1, write down the percentage composition of each element. Step 2, divide those percentages by their atomic masses. That converts percentages into relative numbers of atoms, or what we call moles. Step 3, divide everything by the smallest mole value to normalize the ratio. Step 4, from that ratio, write the empirical formula. Step 5, if you're given molecular weight or vapor density, calculate the multiplier N, multiply the empirical formula by N, and voila, the molecular formula. Picture it like buying chocolate bars for a party. You know the ratio of kids to bars, but once you know the total crowd size, you scale up. Same logic applies here. Let's take the first example. A compound has 40% carbon, 6.7% hydrogen, and 53.3% oxygen. Step 1. Divide each by atomic mass. Carbon 40 divided by 12 gives 3.33. Hydrogen 6.7 divided by 1 gives 6.7. Oxygen 53.3 divided by 16 gives 3.33. Now simplify. The smallest value is 3.33. Divide all by that and the ratio becomes carbon 1, hydrogen 2, oxygen 1. So the empirical formula is CH₂O. That's our recipe ratio locked in. Now let's go one step further. The empirical formula is CH₂O. Its empirical weight is 12 plus 2 plus 16, which is 30. The problem tells us the vapor density is 30. So molecular weight equals 2 times vapor density, 2 times 30 equals 60. Now find N molecular weight divided by empirical weight equals 60 divided by 30, which is 2. So the molecular formula equals empirical formula multiplied by 2. That's open bracket CH₂O close bracket times 2 giving C₂H₄O₂. That's acetic acid. Yes, the acid that gives vinegar its sour taste. From percentages on paper to something on your dining table, chemistry really is delicious. Here comes another one, a bit different. A compound weighs 10.47 grams, containing 6.21 grams of a metal X and the rest 4.26 grams of a non-metal Y. First, calculate percentages. X is 59.31% and Y is 40.69%. Now divide by atomic masses. For X, 59.31 divided by 207 gives 0.286. For Y, 40.69 divided by 35.5 gives 1.146. Ratio time. Divide both by 0.286 and the ratio is x1 to y4. That means the empirical formula is xy4, a neat little salt-like structure. Why do we slog through these calculations? Because formulas tell us the truth about substances. Analytical chemists use them to identify unknown compounds in labs. Fertilizer companies use them to check if nitrogen or phosphorus percentages are right. Pharma companies check drug molecules, and metallurgists test ores and alloys. Even fuel chemists calculate empirical formulas of hydrocarbons to evaluate energy content. So, whether it's your spinach rich in oxalic acid, the medicine in your cabinet, or the petrol in your car, all these formulas start with calculations like these. Powerful stuff, isn't it? Let's bring it all together. The empirical formula is the simplest ratio of atoms. The molecular formula is a multiple of the empirical formula found by using molecular weight or vapor density. The problem solving method is always the same. Start with percentages, convert to moles, reduce to ratios, find empirical formula, and then scale up to the molecular formula. From our examples, CH₂O gave us acetic acid, C₂H₄O₂. The second example gave us a compound with formula XY4. See how logical it becomes once you follow the steps? So, to sum up, never be scared of percentages in chemistry problems. They're just clues, waiting to be converted into the actual identity of compounds. And that's the magic of stoichiometry. I hope this session gave you confidence and maybe even a smile while solving formulas. Catch you in the next class, where chemistry will continue to surprise you in the most logical way possible.